is nuclear waste compatible with a sustainable future? Now, based on whatever knowledge you have about nuclear waste, I would like all of you to reflect on this for the next few seconds before we go into discussing this further. And one of the main reasons we want to ask ourselves this question is because we have been using fossil fuels for more than 100 years now. And as a result, we have emitted a lot of greenhouse gases into the atmosphere, and we now fully understand the environmental impact it has had. But in the same way, we have used nuclear energy for about 60 years now in the United Kingdom. And as a result of that, have created highly dangerous radioactive waste. And we have to ask ourselves this question, that can we deal with this in a sustainable way so we don't end up creating an environmental disaster for our future generations? And it is essentially this moral question that is the basis of my talk today. And what I will try to do for the next half an hour is to give you an overview of what the problem is, what nuclear waste is, and what we as scientists are trying to do to address some of the challenges in dealing with nuclear waste. But before going into the topic of nuclear waste, let's try to understand why nuclear energy is still an interesting option to policymakers and to the government in the UK and around the world. And that is very obvious from this data that you see on the screen. Is, well, one of the biggest concerns we have at the moment is carbon dioxide emissions, and we want to limit these emissions to reduce the impact of global warming. Therefore, there's an urgency to use energy sources which do not have a very high CO2 impact. And the data clearly shows that nuclear energy is one of the best options in that sense. It has the lowest footprint in terms of CO2 emissions. And therefore, in our desire to transition to a CO2-free energy source, nuclear energy is always going to be an option on the table. But it has its own problems. And one of the biggest issues when using nuclear energy is highly radioactive waste. And how do we deal with that? So let's first understand what nuclear waste is and how it is generated. So the fundamental process behind nuclear energy is we use uranium as nuclear fuel in nuclear reactors. It is essentially like we use coal in coal-fired power plants. And this uranium atom reacts with a neutron, and as a result of that nuclear reaction, it will split into smaller atoms, which is what we call as daughter nuclei. And these daughter nuclei are radioactive elements. But in doing so, it also releases energy. And that is the energy that we use in commercial nuclear reactors. But inside a commercial nuclear reactor, this process happens trillions of times in a fraction of a second in a process called as chain reaction. But unlike in a coal-fired power plant where you burn the coal and emit carbon dioxide into the atmosphere, all the radioactive elements that are created during nuclear energy are confined within the nuclear fuel, and they are not released into the atmosphere. So how does it work inside a nuclear reactor? We start with nuclear fuel, which is shown as in this image on the left side on the screen. And this is called a nuclear fuel pellet, and it essentially contains uranium in it. It sits inside metallic pins, and they are put together to form what is called as a nuclear fuel assembly. So it's a lot of fuel pins containing uranium dioxide as the nuclear fuel. And hundreds of these nuclear assemblies sit inside a nuclear reactor pressure vessel, and the nuclear reactions happen. And a lot of energy is generated as a result of these nuclear reactions. So to carry out that energy, we flow water through the core of the nuclear reactor. It takes away the heat. And then it further heats water in a secondary water loop, which is shown in blue color. That then generates steam. That steam is used to run the turbine. That turbine runs the generator. And that's how we get electricity out of the nuclear reactions. But the typical lifetime of these fuel rods is about 3 to 5 years. And after that, they need to be taken out of the nuclear reactor. And when it is done, they contain a lot of radioactive elements in it. And that means it emits a lot of radiation because it contains radioactive elements. And that is highly dangerous to any living organisms. So it needs to be managed in a responsible way. Now, a simple option is, let's package it and store it. And one of the ways that is done is you will essentially put the spent nuclear fuel rods inside a metal canister. And there are different types of metals, such as copper and stainless steel, that could be used to contain these spent fuel rods. And then we will have to deal with it, which we will talk about later. Another option is what is called as reprocessing. Now, what I said is that the spent fuel contains a lot of radioactive elements in it. And there is a desire to extract some of those radioactive elements, because not all of this is waste. There are some useful things in it as well, such as plutonium. Now, in the UK, we had nuclear weapons development program in the past, and that needs plutonium to make those nuclear weapons. So nuclear fuel reprocessing was done very extensively in the United Kingdom to extract plutonium. And the graph in the middle of the slide shows the plutonium that different countries have. And you will see the United Kingdom has the largest stockpile of plutonium in the world. But plutonium is not only used for making nuclear weapons. It has some good uses as well. And one of those is, because it's radioactive, it generates a lot of heat. That means it could be used to power space vehicles, for example. And NASA in the past used plutonium to what is called as radiothermoelectric generators, and you could send them out into space, and they will give you a long-term consistent source of heat. And there's a picture from Martian movie where you will remember the actor extracting the RTG from the ground. And that's one of the good uses of plutonium. But then, after reprocessing, you end up with uranium, you end up with plutonium, and you end up with a lot of residual, highly radioactive elements. And that is called as high-level waste. And that, again, needs to be dealt with. So at the end, we essentially end up with either spent nuclear fuel that hasn't been reprocessed, or if you reprocess, you have high-level nuclear waste, plutonium, and uranium. And all this needs to be managed. So how do we do that? Because it's highly radioactive, no one wants to have it in their backyard. And in the UK, a majority of the nuclear waste and spent fuel is temporarily stored at the Sellafield site, while we are waiting for a more permanent solution. But this all already reflects a responsible way the industry has taken in dealing with it, because we are currently storing it while waiting for a final decision on dealing with it. So what are the different options that have been explored in the past? Well, one of them was space disposal. The idea was simple, let's send the nuclear waste out into the space. And this is very similar to, if you follow the news, in 2018, Elon Musk sent one of his Tesla cars out into the space. And the principle is very similar, that instead of a car, it would be, let's say, a highly radioactive waste canister or spent fuel canister. But as you know, space travel or sending stuff out into space is quite expensive, so it doesn't make a lot of economical sense. Now, another option that was explored by military, not really explored, it was an unfortunate condition that the military ended up with. So United States had a program back in 50s. They had some nuclear sites in Greenland. And they had some nuclear reactors, and eventually the site was closed, but they had all the high-level nuclear waste dumped under ice. And this picture on the slide shows on the left-hand side, the white color here indicates that in 1950s, the prediction was the height of the ice or the level of the ice will continue to grow. There will be more and more snow, so it was safe to have radioactive waste contained within the ice. But more recent projections will show you that the ice is now melting, which is an impact of the global warming. And that shows it in the red, that by 2090, all that radioactive waste that was stored in the ice at the time will be exposed, because our predictions about how the polar ice will behave have changed, and we now know it's melting at a much faster rate. So again, it's not a feasible option. Another option, more of an imagination to put it, was because radioactive waste generates a lot of heat, what if we use these nuclear waste canisters and put them on low melting rocks? So the heat will slowly melt the rock, it will sink inside it, and over time it will get encapsulated permanently. It's very similar to putting a hot object on wax. It will slowly melt it, sink into the wax, and the wax, as it freezes, will permanently seal the object inside it. But in this case, it would have been radioactive waste inside a rock. But again, there are technical challenges with this, and it's not a feasible option. Another option that was explored in the past, now the radioactive wastes have different levels in terms of how radioactive they are. And one of the categories of that waste is called low-level radioactive waste. And in the past, people thought it was perhaps okay to dump some of this waste into the sea, because sea is big enough to probably deal with this waste, and you could just dump it out into the sea. Again, this is a practice that has been discontinued, and there are international treaties in place that stop countries from doing this anymore. So, what is the current solution to dealing with nuclear waste in the UK and around the world? So, let's take a look at this video and see what the government has proposed in the UK.
We've been using nuclear power for more than 60 years. It's part of our everyday lives, with a fifth of our electricity coming from nuclear. Radioactive waste is a byproduct of those benefits. It is currently stored above ground at more than 20 sites, where it is kept safe for the short term to protect people and the environment. Now is the time to manage radioactive waste for the long term. Geological disposal is one of the UK's largest ever environmental projects, which will provide a safe and secure long-term solution for the disposal of higher activity radioactive waste. There is international consensus that a geological disposal facility is the best permanent solution. It is the chosen approach in countries including Canada, Sweden, Finland and France, with some of these countries well on the way to developing their own GDFs. A GDF is a safe, secure and highly engineered facility that will protect people and the environment using the multiple barriers of human engineering and stable rock, working together many hundreds of meters below the surface. Alternatives to geological disposal have been carefully considered, and we continue to keep options under review. At present, they are all either not technically achievable, not environmentally safe, or too dangerous to implement. There are 6 main factors we'll take into account as we search for a site. First of all, safety. Is the rock the right type for a GDF? Of course, we'll be listening to the community, hearing their views, and whether they are willing to consider hosting a GDF. We'll be considering the environment. Is the area suitable for such a facility? And looking at transport. What are the road and rail links like? What about engineering feasibility? Is construction possible? Finally, will the cost of building a GDF at this site represent good value for the taxpayer? There are many benefits for a community.
So, the solution in the UK and around the world is we will take the nuclear waste and we will dig very deep tunnels underground, which will be up to 1 kilometer deep inside the ground. And all the nuclear waste will be stored in facilities such as those. And they are called geological disposal facilities. Now, do we have such a facility in the UK? No, we do not, because the government has decided to engage with the communities, and if a community agrees to have a geological disposal site in their area, only then a facility will be built there. But to convince the communities about the feasibility of a geological disposal site, one of the questions they could ask is, well, if you are going to put the nuclear waste underground and it is supposed to stay there for up to 1 million years, how can you guarantee that it will stay safely there? What if it comes in contact with water? The corrosion starts, the radioactive elements start to come out of the material, go with the water, contaminate the water table, and spread into the biosphere. How do you prove to the community that that is not going to be the case? And I show this picture of corroded water pipes. This is a simple example you could think of. It's a metal underground, and in few years, there will be a significant corrosion of these metal parts. So there is a significant challenge in terms of designing materials that can survive up to 1 million years underground. And we have to prove to the community and to the scientists themselves that it is doable. So how do we decide what materials can stay up to 1 million years underground? Now, back in 80s and 90s, when we had the nuclear reactors and we had to decide about, well, we have this nuclear waste, we have done the reprocessing, we need to deal with this high activity waste now. What do we do? What material do we use to contain this radioactive waste? A simple answer was glass. Why? Because humans have been making glasses for thousands of years. They exist naturally as well. And there is evidence, at least from archaeological specimens, that the glasses that Romans made few thousand years and that have been corroded under environmental conditions are still okay. But then another big positive thing about glasses was the industry was well developed. You see glasses everywhere, wine bottles to the window glass. So there was all the technology there. And the industry decided, well, we have an existing technology. We have evidence, historical evidence from archaeology that glasses could work. And so they decided to melt the radioactive waste along with glasses, and that molten radioactive waste gets poured inside these metal canisters, which is shown on the left-hand side. And that's what makes a high-level nuclear waste canister. And then the idea is to send this waste canister underground. But the question then is, well, water comes in contact with this canister over time because it's supposed to stay there for 1 million years, and it will start to corrode. So we as scientists had to prove that, no, it is not going to happen. Even if there is corrosion, it's going to be very limited. And one of the types of experiments we do is we select a variety of different glasses, of different compositions, and we do controlled corrosion tests in our lab, simulating conditions which are very similar to what these glasses might experience underground in a geological disposal facility. And we interpret those results as to what they mean. Now, here is an example of an experiment of a glass corrosion. Now, in this case, the glass was in contact with water at 90 degrees centigrade to accelerate the corrosion for 21 years. And what I'm showing here is we take a small specimen out of that corroded glass. And if you see on the screen from left to right, what we see is a highly porous structure. So what has happened as a result of interaction of this glass with water, it has started to leach. It has started to dissolve. And as a result, you see in the black and white picture on the right side, there is a highly porous network. Now, is porosity wrong? Is there something wrong with porosity? The answer is yes. The example, for example, is shown of the skin. There is a picture, and we know very well there's a lot of porosity in the skin, and as a result of that porosity, humans are able to release sweat into the outside environment. So there is this continuous exchange of water through these pores. And it means if you had radioactive elements in a glass like this, it is not a safe formulation. But this is the type of research. We study different glasses. We try to understand what makes them resilient, what makes a good glass, and then design that. And here is an example of what we might consider as a much better version of a glass. And I will try to show you some systematic studies of this glass. Now, what you see in the first picture here is a glass that was in contact with water at 90 degrees centigrade just for 30 minutes. And we use electron microscopy to look inside this sample. And what we see is just about 30 nanometer from the surface. So assume that the water is in contact with the top surface. It's just 30 nanometer penetration of water inside. So that means in 30 minutes, 30 nanometer has been affected. I could calculate then how much does that mean for 1 year. And it's written on the first picture that it would mean we will lose about 0.5 millimeter of this glass per year if we had to interpret our results based on 30 minutes of experiment. Then if the canister that is shown on the left-hand side is about 400 millimeter wide, it means it will last about 800 years, which is not good because we want it to survive for 1 million years. But we come back to the same experiment after about 58 days, and now we see there is about 138 nanometer of depth that has been affected by this water. We again calculate how much would that mean for 1 year, and that is 0.0009 millimeter per year. And that means the glass can last up to 350,000 years. Now we come back to the same glass and analyze it after 21 years, and we see it's about 1200 nanometer has been affected by the water, and we calculate how much would that mean in 1 year, and that means 0.00006 millimeter per year, and we can calculate how long will that canister then last, and it means 5 million years. Now the important message here is there's a property called self-passivation. If you look at these glasses in the beginning, in a very short-term experiment, you will see they corrode very fast. But as time progresses, they tend to stop themselves from corroding further, and this is called self-passivation. Materials try to preserve themselves against corrosion, and it is essentially this self-preservation that we are trying to understand and look for materials which are very good at self-preservation. So what do? We do corrosion experiments under controlled conditions. We try to understand how the material will behave. We also look into archaeological specimens and use those projections to predict what might happen in the future for up to 1 million years. And this is how we build confidence in the materials that we design. Now, it can often mean sometimes you also have to go outside to field trips. And there are some pictures shown on the bottom of the screen. There's a location in the east of England, and it's called Seaham Beach. And that beach is littered with a lot of glass. So it's a good field trip for any of you if you want to collect some glasses from the beach. And the history behind that is near that region, there was a factory back in 1800 who used to make wine glasses. And at the end of the day, whatever was left as a scrap glass, they will throw into the ocean. And as a result of these glasses being in the seawater for hundreds of years, they get corroded. And we often will go and collect samples like these and try to understand what is happening as a result of this corrosion in these very aggressive conditions of an ocean water. But radioactivity always has existed in the nature. Where did we get the uranium that we use in nuclear reactors from? And one of the theories behind why the core of Earth is hot is there is consistently radioactivity happening inside the core. And as a result, heat is generated, and that's what keeps it hot. And it's the uranium inside the core that is responsible for that radioactivity, along with other elements. But there are a lot of other radioactive minerals. We get uranium that we use in the nuclear reactors from these natural minerals. And we know these minerals have retained this uranium for tens of millions of years. So the question we have to ask ourselves, can we learn anything from these natural minerals? Can we try to design materials which are very similar to these minerals and try to use them to contain the nuclear waste that we are dealing with? And one of the materials, it's a natural mineral called zirconolite, which is the first picture on the bottom of the screen, is an interesting candidate. And this is a material that we are looking into as a potential material to deal with the radioactive waste in the UK. So here is a sample of natural zirconolite. It has been collected from the environment. This sample, which is shown in the middle, is about 100 million year old sample. It's radioactive. It contains uranium and thorium. So it's an excellent specimen for us to analyze because it's naturally radioactive, contains uranium, which we want to deal with, and we want to look into it as to what has happened to this sample over 100 million year old. One of the issues is these samples in nature don't grow very big. They are just few millimeters to a centimeter big, but they offer us some interesting insights into this material. And the material on the right-hand side is the same zirconolite, but synthesized in our own lab. So let's take a look at what has happened to this material over 100 million year time period. So what we do is we take the sample, the natural sample, and we cut the top of it, which is shown on the second image. And the rectangle on the top is we use electron microscopy to zoom in on this region. And the color picture on the bottom left shows roughly what this sample looks like. The blackish part on the sample is, let's say, the mud that has covered the sample over these millennia. And if we zoom in on the surface in the region that is shown on the picture, you see there's a lot of porosity that has developed in this sample as well. The size of these pores ranges from a few micrometers down to nanometer scale. And as I was saying earlier, porosity usually isn't good because it allows water to go into the material and release the elements out of it. But let's take a look what is inside these pores. Can we see how deep they go inside the material? So we take a section of this material, we cut through it, and try to have an understanding of how deep they go inside and what has happened inside. And the image on the left-hand side shows you these black lines that are crisscrossing this sample from the surface to inwards. And let's take a look what is inside these cracks. And we do electron microscopy, and we can, in that microscopy, do elemental mapping. We can analyze each and every element as to what is present inside these cracks. The red color shows its iron in these cracks. And where does that iron come from? As these materials, the zirconolite, comes into contact with different fluids in the environment, they are usually iron-rich and silicon-rich. And the picture on the left hand shows that these cracks, which are very small, just 5 micrometer in diameter, are filled with a lot of elements. But the blue color is the uranium. And what we see is that the entire specimen has essentially retained all of the uranium. The uranium is still inside the material. But let's take a closer look to what has happened very close to these cracks where the water has penetrated inside the material. And here is the picture on the right-hand side. And what we see is in the blue color is uranium that is still inside the material. And the orange color is zirconium. So what has happened in this small, narrow channel, which was penetrated by the water, is a very small thickness has lost uranium for it. But the rest of the material has pretty much retained all the uranium. Now, it's just 250 nanometer thick region. And I want you to put that in perspective. The typical thickness of a human hair is 100,000 nanometers. And the thickness of this layer is just 250 nanometer. So very minute amounts of uranium has been released from this material. What it shows you that even if this material has been degraded under environmental conditions for up to 1 million years, it is a highly residual material. It shows it can retain uranium in it the question we have to ask ourselves, well, there is enough evidence in the nature which shows you that materials such as these can contain radioactive elements, but they don't grow very big in nature. They are just few millimeters or centimeter long. And we have a technological challenge. Can we design these materials on an industrial scale? And in fact, we can do that. So again, we see in this case, even if this material has been in contact with environment for 100 million years, it still preserves itself. And again, the self-preservation, we see it in nature, not only in controlled experiments that we do in the laboratories, but in nature, minerals protect themselves against corrosion. So how do we deal with the radioactivity? Well, the best solution I have is we look into the nature. Nature has done it already for millions of years. Why not learn from the nature? And why not try to design the materials as nature has presented to us? And that is the most sustainable way of doing it. So I come back at the end to the same question. Is nuclear waste compatible with a sustainable future? And this is something I want you to think about as you go home in the next few days and months, and whatever you have heard from me and seen from me, and make up your own mind. For me, to answer this question is yes, we can do it. There is evidence in the nature. All we have to do is follow the nature, design the materials at an industrial scale to contain the radioactive waste, and that is the most sustainable way of doing it. Thank you very much.
I suppose my first question is, how did you get into this area? How did you make the links, and how did you sort of begin on your research journey?
All right, I think if I had to go back to, let's say when I was a kid, I think one of the first exposures I had to the nuclear sector in general was a book. It was on nuclear reactors. And it was a book from USSR. And they had a publisher called Mir Publishers. And it was the name Mir, because my name is Mir, and that attracted me. And I thought, well, there are books which are being published with my name, and why not take a look at it? And so I looked into this book. It was on nuclear reactors, and that's my first fascination about nuclear reactors in general. I never thought as to what my final goal will be, as to what I will be studying in the end. But this set me on a track to study nuclear in general. And then I went on to study physics and mathematics back in India. Further on, then I went to France to do a PhD on nuclear waste. And it was, I would say, a combination of luck and chance. I didn't necessarily plan it. And then I continued with the research here in the UK. But what fascinates me is, as you continue to do the research, you see the interesting stuff, and you want to continue further and further. So it's this continued motivation that sort of keeps me doing what I'm doing, and not necessarily the planning that I did 10 or 20 years ago.
And I mentioned at the start, you work in the Miami facility. So that's not based in Florida, it's here at the University of Huddersfield. Can you just explain what Miami stands for?
Yes. So I work at a facility called Miami. Now, Miami is microscopes and ion accelerators for materials investigation. Now, what we do is the materials that are used inside, for example, nuclear reactors or for nuclear waste, or a lot of materials used in space, they experience radiation damage. So there's a radiation in outer space, for example, and that can damage the materials. And we want to understand how these materials change over time as they are being affected by this radiation. So we have a microscope, and we have these ion accelerators which allow us to simulate and see in real time inside a microscope what happens to these materials. And this is what the facility is, and we have a lot of researchers working on different types of materials, whether they are used in space, inside a nuclear reactor, or for the nuclear waste, and try to understand how these materials change over time.
And it's possibly one of the biggest research physical facilities on campus, but actually you look at the smallest, tiniest things with your microscopes, don't you?
Absolutely.
I find it fascinating.
And it is the only facility in the country, so it is a very novel piece of sort of experimental kit.
Brilliant, brilliant. I'm going to see if we've got any questions from the floor first. Is there? Great, we've got one there. Right, I'm going to try and summarise that question for the live stream. So do butt in if I don't quite get it right. So I think the question's around, there's obviously a huge amount of money and infrastructure that's required to deal with this and make it a viable technology. Are you concerned that if other places follow the lead because of the research that you're doing, they might not have the financial stability and infrastructure, and maybe there are other areas that they could be looking at?
Thank you for the interesting question. I think, yeah, it is a very important question for the UK and for other countries to think about. Now, what we have to, I think, what's very important to consider is one of the biggest costs that is associated with nuclear in general is when we factor, so you design the nuclear reactor and you decide the electricity costs, the eventual disposal, the costs of that are factored into the electricity costs. So you are already paying for its long-term management. Now, if you compare that with fossil fuels, you are now just thinking about putting carbon tax, which you already haven't paid for the previous 40 decades, right? So if you sum up all the money that you will need actually to deal with the issues of dealing with carbon dioxide or other issues with that, and add those factors, then there is a parity between the nuclear power because it maintains a sustainable management of the waste that it generates, which is not the case with other sources of the energy. You factor in those and you are at a parity. But at the same time, you have to understand what is the implication of not going, for example, nuclear. And if we want to reduce the carbon footprint, there is an MIT study which shows that almost 80% of the scenarios, if you want to limit the carbon dioxide emissions in next 30 to 40 years to an acceptable level, nuclear has to be an essential part of the mix. So it's a choice between, do we say, well, it's going to be a bit expensive, so let's destroy the environment, or do we say, well, we have a responsibility, like we are paying the carbon tax? Well, that's already included in the nuclear power because it's done in a sustainable way. So there's a balance that is to be maintained.
Okay, thank you. Have we got any questions? Yes. Okay, so that's a good question. So the experiments that you're doing to test these materials are quite short term. How confident are you in those results to then extrapolate to be relevant to the millions of years that you need to consider?
Yeah, absolutely. It's a fantastic question. And this is what anyone, even if you go out to the community that, well, we want to host a geological disposal, the question they might ask, well, your experiments are just a few years long. How do we know it will survive 1 million year? And this is why, as a scientist, we do not just focus on observations. We focus on fundamental understanding. And when we do, so one of the experiments I showed was 21 years. It was one of the longest experiments that you can do under controlled conditions, right? And this is why you can do controlled experiments under controlled conditions, and you develop a fundamental understanding. But then you go out into nature. And this is why I presented this example of extracting the mineral from the nature, which has already been there for hundreds of millions of years. While our criteria for dealing with nuclear waste is, let's say, up to 1 million years. We want to make sure it stays safe up to that time period. But we can extract samples from nature which have been there for much longer. So what we often do is we will design same or similar material in the lab. We will test it under short-term experiments. We will develop a fundamental understanding. We will use that understanding to extrapolate to these natural samples which have been in the environment and see, does it make sense? And that's how we build confidence, by learning from nature itself and using our fundamental understanding of the processes that we get from these controlled short-term experiments.
Great, thank you. Really good question. We've got a question from the live stream. That's a good question, isn't it? So how will you maintain or guarantee that the GDFs won't be subject to external vibrations such as earthquakes, transportation, industrial vibrations that are created?
Well, again, an excellent question. Now, typically, the vibrations from transportation are not a big concern because the GDF is expected to be 1 kilometer underground, where any surface-related transportation will not have a huge impact on that. But vibrations, for example, as a result of earthquakes is a concern. And this is why when the geological survey of the country is done, and which has been done, you have to locate within the country what are the safest regions from the perspective of earthquakes. And this is the first part of the survey. So this is why when we decide as to where the site will be hosted, there are multiple factors, and one of them is it should be geologically safe. And you look in the past, what is the history of earthquakes in this region, what are the future predictions, and on that basis, you will select a site where you don't have a possibility of having an earthquake in the next few million years. The biggest concern we have is, well, you design the geological disposal site, it's to last 1 million years. We are not going to be there, right? There will be different people. How would they know what is underground there? And what if they do something wrong? And one of the biggest safety concerns is, what if someone drills in that location in the near future? Thank you.
Thank you. So if in the future people decide that actually that nuclear waste would be really useful, obviously if it's out in space, it would be very difficult to retrieve. But how reversible is the process that you're looking at?
Yes. So again, an excellent question. This is essentially a policy that is defined by the government. And different countries have different policies with regards to the retrievability of the nuclear waste. The policy in the United Kingdom is the site should be such and the design should be such that the waste is retrievable.
Okay.
Different countries may have different policies. I think France probably has an irretrievable policy. And the reason you want to have the possibility of being able to retrieve the nuclear waste is, what if during the design phase or soon after the site was closed, something happens wrong, and you need to mitigate those factors. So you need to have the possibility of being able to retrieve the waste and rectify any errors. So the policy in the UK is retrievability.
Okay, thank you. We got any more? One from the live stream there. So this question's about, we've looked at the porosity with respect to water. Have you considered any other chemical reactions from other minerals which might be pertinent to the process?
Yes. So when we do safety analysis, one of the approaches is, let's assume the worst happens. Now, what's the worst that can happen? Well, you put the glass or the nuclear waste in water and all of it dissolves. That's the worst case scenario. And we base our safety analysis on the worst case scenario. And you make the design as per that. But even a better situation is, in principle, it's not going to come in contact with water straight away. And we design multiple barriers around it. So you will have the waste canister surrounded by metal. Outside will be clay surrounding the canister, and outside that will be the rock. And the reason you want to use clay is it's sort of impenetrable to water. After a certain depth, water can penetrate, but it doesn't allow water to penetrate, and that prevents the water from coming into contact with the canister and stop the corrosion. But it also means there is this complex interaction where the minerals or the elements that are coming from the clay, from the metal canister, they create a complex reaction environment. It's not the reaction happening in pure water now. It's a reaction which contains clay, which contains the oxides and other elements from the canister, and they have an impact on the rates of corrosion. And this is also an area we are researching as to what the impact of this chemical environment is. But the focus always is on what is the worst that can happen, and let's design for that worst case.
Very good. We've got another one from... so this question is about fusion. So does nuclear fusion make this obsolete?
Well, I think fusion has advantages in terms of the waste. One of the big issues, for example, with nuclear fission, which is what I was talking about, is uranium atom splitting into smaller atoms, and those atoms are radioactive. And in the process of this fission, you end up essentially with elements that are present in the periodic table, a whole lot of elements, so a lot of highly radioactive elements. And it is that aspect that in the nuclear fusion, when the reaction happens, you do not end up with this complex radioisotope. But the materials that will be used to build the nuclear reactors will still be subjected to some activation or certain nuclear reactions from neutrons, for example. And that will lead to some activation, some generation of certain level of radioactivity. But that is going to be very small compared to what we are dealing with fission. So in the sense, the issue of dealing with these high levels of radioactive waste is fission specific and not necessarily fusion. But that being said, there will be certain low levels of radioactive waste in nuclear fusion as well.
Okay. Any more questions from the floor? No, I'd like to finish with one then.
I think there's probably a question there.
Oh, sorry, no, go ahead. Yeah, so that's a really good point. And so the question's around, when do we engage public consultation with the scientific community to build a better understanding for communities, not just of the science, I think, but of the potential risks and the potential benefits?
Yes, absolutely. This is a critical question because in the UK, we don't have a nuclear disposal site decided yet. Now, what has been done is certain sites have been identified in the UK as the potential future disposal sites. Some, for example, in West Cumbria, this is a region that is of interest from the perspective of geological disposal. And from last 2 to 3 years, consultations have already started with government representatives. There is a nuclear waste service is, let's say, the official representative to deal with the nuclear waste and with the public, and they have set up certain engagements with these key communities. It's about 3 at the moment, 4 that have been identified as the potential sites, and engagement centers have been already set up to try to convince the public in those regions, based on the scientific evidence there is, that this is a safe approach. But there is always going to be some negative perceptions about nuclear energy, which stem from the issues with nuclear waste, nuclear accidents, and this engagement has started. This lecture is, let's say, aimed towards that, but there is this more and more engagement happening in the UK, and we hope that we will try to, based on the science, clarify some of these issues, and communities will agree to host a site in the UK.
Okay. Oh, sorry, we've got another one from the live stream. That's a good question. What would you advise somebody who would like to work in this area?
Yeah, absolutely. I think it's the right time to work in this area because we designed nuclear reactors 50, 60 years ago. They have come to the end of their lifetime. And now the process of dismantling them and dealing with the nuclear waste is the next job. This decade will be the decade where we will have to deal with these issues and decide on what we do. This is an absolutely fantastic time for people who are interested in key issues such as dealing with nuclear waste to engage in the science, to scientists, and to develop their understanding and research in this subject, because by doing so, they will be working on an issue which has a very high social impact.
Mm-hmm. Yeah. And I think from your talk, what I gained from that is an insight into the vast diversity in scientists, engineers that are going to be required to solve this issue and solve this problem. So it seems to me like there's jobs for millions of years for a lot of different people.
Well, absolutely. I think once a site is chosen, it is expected that to implement the full geological disposal in that area will take about 100 years. So that community will have, let's say, a scarcity of jobs at least for 100 years. It's a long-term project. But at the same time, I remember last year there was a community engagement in somewhere in the east of the country about this, and the experts were telling them, this will bring a lot of long-term investment, and some people thought it was essentially bribing them. Right? Because there is still mistrust, there is still lack of understanding, and if you tell people it will provide you long-term sustainable jobs, they might doubt you. But this is a fact. It is a long-term project, and it will bring long-term sustainable jobs in that region.
And hopefully people, doing research like you makes it accessible, but also ensures that we're safe going forward. So
absolutely.
Brilliant. Okay, so thank you very much, everybody, for your participation and some brilliant questions. And once again, thank you so much for a very insightful talk. It's given a lot of people some things to think about, I think. So thank you.
Thank you very much.